Welcome to the class. Our topic of discussion is gas mixture. This topic has concern for our present study of steam power plant, since in the steam power plant, in the condenser, actually we will have cooling tower as well. So in the cooling tower we will have air and water vapor as their mixture. So their air will be also treated as a gas and water vapor will also be treated as gas. So the mixture will be present over the air. So the mixture properties we would have to calculate. So this class or this topic of gas mixtures will let us know how to find out different mixture properties from the known properties of individual gases. So let us start. We know that for any ideal gas we have P into V is equal to N RU into T, where we have RU as universal gas constant and this N is number of moles. Then P is pressure, V is total volume and T is temperature. So we have one more relation which says that PV is equal to MRT, where R is particular gas constant and here we have M as mass. So if we divide both the equations, we get small r or particular gas constant is equal to universal gas constant divided by molecular weight, since M is equal to molecular weight into number of moles. This is weight of 1 mole of a gas into number of moles. This gives us mass. So practically when we write PV is equal to MRT, we are writing PV is equal to mu N into RT, and then that is why we get universal gas constant is equal to molecular weight into particular gas constant. So we say that particular gas constant is equal to universal gas constant upon molecular weight. So then if we have a gas, which is mixture of many gases. So let us consider this is a container which has a mixture of many gases. So what will happen? We can say here that this mixture has mass mm, this mixture has pressure P, this mixture has temperature T. So mixture mass is equal to mass of all species which are present. So it is equal to I is equal to 1 to small n. So m1 plus m2 plus mn. So if there are n components in the mixture, then there will be summation of all n masses to get the mixture mass. So we can write down mass fraction of any one species, say 1 mf1, which is called as mass fraction of species 1 is equal to m1 divided by mm. So in general mfi is equal to mi divided by mm, or is equal to mi divided by sigma mi. Similarly, we can also find out mole fraction, where we have yi is equal to ni divided by nm, where this is called as mole fraction, where ni is equal to number of moles of a component of mixture and Nm is equal to N1 plus N2 plus Nn is equal to sigma Ni, that means total number of moles of mixture. So this N1 is number of moles of first component, so that divided by number of moles of mixture will give us mole fraction of one component or first component. So we can find out molecular weight of mixture is equal to mixture's mass divided by number of moles of mixture. This is the molecular weight of the mixture. Then we can write down here mass fraction of any species I is equal to Mi divided by mixture mass, where mass Mi can be written as molecular weight of I into number of moles of I divided by molecular weight of mixture into number of moles of mixture. So we can write down this as molecular weight of I divided by molecular weight of mixture into Yi. So this is the relation between mass fraction and mole fraction. Further, we can find out other relation where we can write down molecular weight of mixture is equal to mass of mixture divided by number of moles of mixture. So mass of mixture is Ni into mu I sigma, number of moles is Nm. So this is sigma Ni upon Nm into mu I. So molecular weight of mixture is sigma Yi mu I. So this is what molecular weight of mixture. We should remember one thing, that summation of mole fraction of all species is equal to 1 and summation of mass fraction of all the species is equal to 1. Summation of mole fraction is also 1. We can also write mixture molecular weight is equal to, this is one relation, there can be other relation as well, divided by number of moles. So this is mixture mass, number of moles of mixture can be written as molecular weight of mass of I divided by molecular weight of I. So this is basically Ni and this is summed over all I's. So this is Nm. Sigma Ni is Nm. So then we can have 1 upon mu I into Mi upon mm. So we can write it down as 1 upon sigma mfi upon mu I. So this is the formula for molecular weight of mixture. Now we know that if we know all the masses, then we can find out mass fraction. If we know all the moles, then we can find out mole fraction. Then we should also be able to find out the properties from the known mass and mole fraction. The properties like mixture's internal energy, mixture's entropy, mixture's enthalpy and mixture's internal energy. These things can be calculated from the individual known mass fractions and also from the individual known basically properties like entropy, internal energy, enthalpy. So that way we should know, suppose Um is internal energy of the mixture, then it is equal to Ui, which is summation of all internal energies, and then into, then what we can do, this Ui is extensive, we can make it as intensive, then we can basically write it as Mi into Ui. This is specific internal energy of ith component into mass of ith component summed over all component will give us internal energy of mixture. Similarly, mixture's enthalpy is equal to sigma Hi is equal to sigma Mi small hi. Now we are not needing the extensive internal energy or extensive enthalpy, we need intensive properties, and then in that case we should write down as Mfi into Ui. So mass fraction into internal energy of one species and then summed over all species will give us specific internal energy of the mixture. Similarly, we should also find out Cp, which is specific heat at constant pressure, Cv, specific heat at constant pressure for the mixture using this formula Mfi Cpi and then Mfi Cvi. So this is how we should be able to find out all the mixture properties. Now this we can make use of to solve some examples. So let us see some examples over here. So first example says that consider a gas which contains 3 kg of oxygen, 5 kg of nitrogen and 12 kg of CH4 methane. Find mass fraction of each gas, mole fraction of each gas, average mixture molecular weight and gas constant. So in this we are given that O2 has, suppose M1 as 3 kg, we have N2 then which is M2 as 12 kg, we have CH4 which is M3 as N2 is 5 kg and CH4 is 12 kg. Then we know we can find out the mixture mass first, which is M1 plus M2 plus M3 or sigma Mi I is equal to 1 to 3. So we get mixture mass is equal to 20 kg. Now we should find out basically mass fraction, which is simple to find out. We can find out Mf1 is equal to M1 divided by mm, so it is 3 divided by 20, so it is 0.15. Then Mf2 is equal to M2 divided by mm, so it is 5 divided by 20, so it is 0.25. Then Mf3 is also can be found out by two ways. First way is we are saying it as M3 divided by mm, which is 12 divided by 20, which is 0.6, or otherwise Mf3 can also be found out from the fact that which is Mf1 plus Mf2 plus Mf3 is equal to 1. So Mf3 is equal to 1 minus Mf2 minus Mf1. So also Mf3 is equal to 0.6. Now having said this, we can find out number of moles of oxygen by knowing mass of oxygen, which is mass of 1 divided by molecular weight of 1. Mass of 1 is given as 3. We know molecular weight of diatomic oxygen is 32. So we have 3 divided by 32, which is 0.094, which is number of moles, number of kilomoles. Since it is in kg, we have kilomoles of oxygen, and then N2 is equal to M2 divided by molecular weight of 2, which is 5 divided by 28 is the molecular weight of nitrogen. So 5 divided by 28. So we have this, So it is 0.179 kilomoles. Similarly, N3 is equal to M3 divided by mu 3. So it is 12 divided by 16. So CH4 has molecular weight as 16, which is 12 for carbon and 4 for hydrogen. So 12 plus 4, 16. So 12 by 16 is equal to 0.750 kilomoles. So we can find out Nm is equal to N1 plus N2 plus N3, which gives us 1.03. So we can find out mole fraction of first species, which is Y1, which is N1 divided by Nm. N1 is 0.094 divided by 1.23, so it is equal to 0.092. Y2 is equal to N2 divided by Nm. N2 is 0.179, Nm is 1.023, so this is equal to 0.175. So Y3 is equal to 1 minus Y1 minus Y2 is equal to 0.733. We could have as well used Y3 is equal to N3 divided by Nm, and N3 is 0.750 divided by N3 divided by Nm, 1.023, and then also we get 0.733. So this is the way we just found out mass fraction and mole fraction of each species. Now we have to find out average molecular weight. So we know we can find out mu mixture is equal to sigma mole fraction of a species, which is basically yi into mu I. This is one way. We know yi, y1 into mu 1, so it is 0.092 into 32 plus 0.175 into 28 plus 0.733 into 16, and this gives us mixture's molecular weight as 19.6 kg per kilomoles. So we can as well use mu m is equal to mass of mixture divided by number of mole of mixture. So mass of mixture is 20, number of moles of mixture is 1.023, and this will also give us close to 19.6. Now our aim is to find out gas constant, and we know gas constant for the mixture would be universal gas constant divided by mixture's molecular weight. So universal gas constant is 8.314 kilojoule per kilomole Kelvin divided by (19.6) kg per kilomole, and this gives us 0.424 kilojoule per kg per Kelvin. So this is how we would have solved the example based on the mass fractions of or masses of different components for a given mixture. So let us solve the other example, which says that mixture of O2, CO2 and helium gases with mass fractions 0.0625, 0.625 and 0.321, respectively enter in a gas turbine at 1000 kilopascal and 600 Kelvin. This mixture expands till 100 kilopascal. Isentropic efficiency of turbine is 90%. Find specific heats of mixture and work output per kg of mixture. Consider the following values of specific heats. Basically they are given in the table for each component, and assume them constant with respect to temperature. So here Cp and Cv both are constant, so gas is ideal for us, and we will again say O2 is equal to 1. So we are given with MF1 0.0625, we will say CO2 as 2, and this is equal to MF2 and it is 0.625. Then we have helium which is 3, and we have MF3 and that is 0.3125. We can cross verify by making sigma MFI, it will give 1. Actually this data of MF3 or any one MF is redundant, since we could have as well calculated that. Then we will sketch for turbine, and then we can notice that this is what it is happening. We know state A and we have to find out state B. This is turbine. So first, for that we know that turbine output is difference in enthalpies, and enthalpy of a gas is Cp into T. So Cp into Ta, so work done in the turbine is Cp of mixture into Ta minus Tb. So we need to find out Cp of mixture. So for that we can say Cp of mixture is equal to sigma MFI Cpi. So we know it is MF1 is 0.0625 into 0.918 plus 0.625 into 0.846 plus 0.3125 into 5.1926. So this gives us CPM, which is the mixture specific heat at constant pressure, as 2.209 kilojoule per kg Kelvin. We also know that the pressure ratio and temperature would have a gas constant also associated with that. So for that, let us calculate mixture specific heat at constant volume, which is again MFI into CVI, which is 0.0625 into 0.658 plus 0.625 into 0.657 plus 0.3125 into 3.1156. So we have CVM as 1.425 kilojoule per kg Kelvin. So we can know two things. We can know R of mixture, which is Cp of mixture minus Cv of mixture, and this R value is 0.7836 kilojoule per kg Kelvin. Similarly, gamma is equal to Cp mix divided by Cv mix, and so we have gamma is equal to 1.55. Knowing that, we can find out the temperature basically. So we have T2 dash, which is the ideal temperature at the exhaust of the turbine, so we call it as TB dash upon TA is equal to PB upon PA bracket raised to gamma 1 upon gamma. So which is equal to, as we know, turbine entrance condition is 1000 kPa and 600 Kelvin, and bottom or end of the turbine is 100 kPa. So we can say it has 1000 kPa divided by basically 100 kPa divided by 1000 bracket raised to gamma g minus 1 upon gamma g. So this gives us Tb dash is equal to 1 upon 10 bracket raised to gamma g minus 1 upon gamma g into 2a. So we can get Tb dash is equal to 265.0 Kelvin. So we know efficiency of turbine is Tb minus Ta divided by Tb dash minus Ta. Turbine efficiency is given to us, so we can write down Tb is equal to Ta plus efficiency into Tb dash minus Ta. So we have Tb is equal to real temperature at the exit of the turbine is thus 298.5 Kelvin. So now we can find out turbine work is equal to Cp mixture into Ta minus Tb. So we know now Ta is 600 degree Celsius or 600 degree Kelvin, 600 Kelvin, and then we know now Tb as 298 Kelvin. So using that we can find out Cp into Ta minus Tb, and we get work output is equal to 666 kilojoule per kg. So this is how we can solve the example for the mixture. We were asked in the example to find out specific heat of the mixture and work output per kg of the mixture. So we found out work output. Work output could also have been found out as turbine work into Cpm into Ta minus Tb dash. So that would also have given into efficiency, that would also have given 666.0 kilojoule per kg. So this is how we end the discussion on the gas mixtures. Now we have understood if the individual properties are known and fraction of each component are known, we can fetch the properties of the mixture. Thank you.